Welcome, fellow adventurers, to the Nerd Teach Guild Hall. Today, we are embarking on a quest to master the truly arcane art of backtracking. Now, this isn't just another algorithm. It's a powerful way of thinking, a mental tool that can help you solve some of the most treacherous, most complex problems in all of computer science. So sharpen your wits. Let's begin.
Every great quest starts with a formidable challenge, right? Ours is no different. We're going up against what are known as combinatorial problems. And you can think of these as the giant, terrifying beasts that guard the treasure we're all seeking. They're problems with an almost unimaginable number of possible solutions.
And this is our monster. Its name, Combinatorial Explosion. It's a foe that presents us with a near infinite number of possibilities. For every single choice we make, it feels like 1,000 new paths, 1,000 new faces of the monster appear. Trying to fight this thing head-on, it's pure madness. So how in the world do we even stand a chance?
Well, you've got two choices. On the one hand, we could be the bumbling giant. This is the brute force approach, just blindly smashing every single path, checking every possibility one by one. It's strong, sure, but it's not smart, and it will absolutely exhaust itself and fail against our trillion-phase monster. Or we could be the wise algorithm answer, using the elegant, subtle magic of backtracking to intelligently eliminate impossible paths before we even waste a single step walking down them.
This quote here, it frames our magic perfectly. See, backtracking isn't about avoiding the fight. It's about fighting smarter. It still systematically explores every possibility, but it does it with the wisdom to know when to give up on a bad idea and try something else. It's an exhaustive search, yeah, but it's an intelligent one.
So how does a wise algorithm answer begin their journey? They don't just charge in swords swinging. No. First, you need a map of the dungeon. And for us, that enchanted map is called the State Space Tree.
I want you to think of the state space tree as this magical, all-knowing map. It doesn't just show you the physical layout, it represents every single possible path, every choice you could possibly make, and every potential outcome of your quest, all laid out at once. It's the literal blueprint of the entire problem. So let's look at the anatomy of our map. The root, that's the dungeon entrance, our initial state where we begin our adventure. The edges are the hallways we can choose to walk down, our choices. The internal nodes, those are like partially explored rooms. We've made some progress, we have a partial solution. And then, at the very end of the hallways, you have the leaf nodes, and they're one of two things, either treasure, a valid solution, or a dead end. Now, we don't just wander aimlessly on this map. We have a strategy, and it's called depth first search, or DFS. What this means is we pick one hallway and we follow it as deep as it possibly goes. We commit to that path until we either find treasure or we hit a brick wall. And only then do we backtrack to the last intersection and try a different hallway. But just having a map isn't enough to make us a master algorithmancer. Our real power, it comes from a magical artifact we acquire along the way. A tool that lets us see which hallways are traps without ever having to set foot in them. Let's call it the truth lens. Now, in the old, dusty, arcane texts, this is called a promising function. But let's be real, truth lens is way cooler. It's basically a set of rules or constraints for our quest. At any point in our journey, we can hold up this lens, look at the path we're on, and it will tell us if this path could possibly lead to treasure. And here's what the lens shows us. A promising path. It glows a vibrant green. It's telling you, keep going, adventurer, treasure might lie ahead. But a non-promising path, that glows an ominous red. It's a guaranteed dead end. The lens is screaming at us, turn back now. There is absolutely nothing for you down this hallway. Okay, this is the crucial part. When our truth lens shows us that red, non-promising path, we don't just turn back. We perform an act of incredibly powerful magic called pruning. We magically seal off that entire hallway and every single room, hallway, and dead end connected to it. We don't waste a single second exploring it because our lens has guaranteed it's fruitless. And the power of this magic it's just staggering. Don't let the formula intimidate you. All it's saying is that if B is the number of choices you have at each step, and N is how deep the solution is, pruning just one bad path early on can eliminate millions, sometimes even billions, of dead ends we never ever have to visit. This is how the wise algorithmancer defeats that trillion-faced monster. Okay, let's pause for a second. Let's make sure this is clicking. Imagine you're solving a Sudoku puzzle, a classic backtracking dungeon, right? At what exact moment does your truth lens glow red? Think about it. It happens the instant you place a number that breaks the rules. Like putting a 5 in a row that already has a 5. That's a non-promising state. That's your signal. That's when you prune.
All right, so we have our map, the state space tree. We have our magical artifact, the truth lens. Now, we need the spell itself, the ritual that lets us walk the dungeon, make choices, and retreat when we need to. And it's actually a simple but incredibly powerful 3-step incantation.
Here are the 3 rituals. It's a loop. First, you cast the spell. You make a choice. You apply a move. You take that step down a new hallway. Second, you enter the mirror realm. This is recursion, where you call upon the same spell again from your new position, going deeper and deeper into the problem. And third, and this is the most important step, you rewind time. You undo the move, stepping back to exactly where you were before.
So let's decipher this ancient scroll together. If is solution is simply asking, hey, have we found the treasure yet? The for loop for candidate and candidates is us looking around at a crossroads, wondering, okay, which hallways should we try next? Apply move, that's the moment we commit. We take a step forward.
Backtrack state is the powerful recursive spell, entering that mirror realm of deeper choices. And finally, undo move. That's the crucial magic of rewinding time, of erasing our footprints so we can try another path.
I really want to drive this home. This rewind time step, the undo move function, that is the secret sauce. That's the heart of backtracking. It's what gives us the courage to explore so aggressively. We can go deep down any path, no matter how crazy, because we know we can always perfectly reverse our steps and return to a crossroads, leaving no trace, completely ready to explore the next option. It makes exploration cheap and fearless.
And just like that, you've done it, Algorithmancer. You have the map, you have the lens, and you have the incantation. You are ready to go out there and claim your treasure. But true mastery, as always, means understanding the limits of your own power. And this power is incredibly practical. This isn't just for games. Your new spell can conquer so many different realms, from classic puzzles like the N-Queen's problem in Sudoku to really complex real-world challenges. Imagine designing the most efficient circuit board or finding hidden patterns in vast sequences of DNA. That is the true power of backtrack.
But here is the wisdom you must always carry with you. This magic is only as powerful as your truth lens. If your promising function is weak, if it doesn't prune branches effectively, then you're not a wise algorithmancer anymore. You're just a bumbling giant again, exploring far too many useless paths. The real key to mastery is designing a sharp, effective truth lens for your problem.
So let's just step back and review the amazing treasure you've won on today's quest. You've gained the dungeon map, the ability to visualize any problem as a state space tree. You've forged a powerful truth lens, the magic of pruning. You've mastered travel through the mirror realm of recursion. And, most importantly, you have learned the art of the wise retreat, the very core of backtracking itself.
Welcome, apprentice algorithmancers, to the Nerd Teach Artisans Guild. Today, you're not just learning, you're undertaking your masterwork. We're going to forge one of the most fundamental patterns in all of programming.
So what is this grand task? It's about pure creation. We're going to take a handful of components and craft every single possible combination from them. Master this, and you'll be ready for anything that Royal Coding Trials can throw at you. So yeah, let's fire up the forge and begin.
So this epic quest has a name. We call it Forging the Power Set. It's a pretty cool name, right? It's the sacred collection of every single possible subset you can make from a given set. Let's really dig into what that means.
Okay, so here's the first mind-bending part, the scale of this thing. If you've got a simple set like 1, 2, 3, you might think there are only a few combinations, but the power set contains 2 to the power 3, which is 8 possible little constellations, and that includes everything from the empty set, which is kind of like the void, all the way up to the set with all 3 elements in it. So how on earth do we create so many possibilities from just a few items? Well, the secret lies right here, at the heart of our workshop, the binary forge. This is where it all begins, with a simple but incredibly powerful choice for every single element we have.
For each element that comes across your anvil, you get to wield one of 2 primal spells. You can cast the gold Include spell, which summons it into the subset you're building. Or you cast the silver Exclude spell, which leaves it out. That's it. It's just a simple, fundamental binary choice, in or out.
And that choice is the whole secret. That's why there are always 2 to the n subsets. Because for each element, you're making a decision that splits reality in 2. It grows this huge tree of infinite choices. Every single path from the root of that tree down to a leaf is one of your final, unique subsets. It's a fundamental law of this craft.
So this right here, this is the core pattern, the secret handshake of our craft. We call it the backtracking template. You look at an element, you cast the Include spell, and you dive deeper down that path to see what happens. But then, and this is absolutely crucial, you have to cast the unsummoning incantation. You have to undo that choice. This lets you step back, backtrack, so you can then go explore the other path, the Exclude branch.
All right, enough with the magic metaphors. Let's translate this into actual code. But you gotta be careful. The incantations you use are different depending on what programming realm you're in. C++ and Java, for example, handle the whole process very, very differently. In the world of C++, think of it like you're weaving one single living tapestry. The vector you're building gets passed around by reference, and you're just adding to it and taking away from it directly. But Java is a bit more fickle. With Java, you have to think of it like taking an instant portrait, a snapshot of your subset every time you find a valid one. In C++, that unsummoning incantation we talked about is super direct, super powerful. It's just pop_back. After you've explored a path with an element, this spell literally removes it from your vector. It cleans the tapestry, restores everything perfectly so you can go explore the other branch. It's a manual undo, but it's really precise.
Okay, listen up, because this is a classic apprentice mistake in Java. You absolutely have to cast the snapshot spell. If you just add your temporary list to the results, you're not adding a copy, you're just adding a pointer to it. And as you keep backtracking and that list becomes empty, all of your saved results will magically become empty too. It's a disaster. You have to cast new array list to create that permanent instant portrait.
Okay, you're getting it. You're really getting the hang of this. But now it's time for a new trial. What happens when your starting materials aren't unique? What if you're given what we call twin spirit gems, like in the set 1, 2, 2? Well, your current forge is going to create a bunch of phantom duplicate constellations. We can't have that.
The ritual to fix this has 2 parts. First, you have to align their energies by sorting the input array. That just gets all the identical gems sitting right next to each other. Second, you have to learn to prune the future. You add a special check into your spell work to stop yourself from going down duplicate paths. And this line of code right here is the pruning incantation. You need to burn this into your memory. It basically says, hey, if the gem I'm looking at is the same as the one right before it, and I've already considered including this gem, then I'm just gonna skip it. This one little line shatters all those duplicate branches before they even have a chance to form. It's beautiful.
So you've been honing your craft on these abstract, mystical sets, and you're probably wondering, okay, cool, but what's the real point? Well, now I'm going to show you the true industrial power of this skill. Let's step into the crucible, where this algorithm can solve a massive, real-world problem.
I want you to imagine a huge, modern software kingdom. Its behavior is controlled by 50 different feature flags. You know, little on-off switches. Now, if you wanted to test this system completely, you'd have to check every single possible combination of those flags being on or off.
So how many combinations is that? It's 2 to the power of 50. That's over a quadrillion. Let that sink in. A quadrillion different states. This is what we call the dragon of many heads. It's an impossible testing challenge. No company, no guild on Earth has the time or the money to fight every single one of those heads.
But here's the secret. The guild wisdom that's been passed down from senior engineers for generations. Most bugs, they're not caused by some bizarre interaction of 17 different features all at once. Nope. They're usually caused by the simple interaction of just 2 things. That is the dragon's weakness.
So, using a clever technique called pairwise coverage, which is really just an adaptation of the algorithm you just learned, we don't need to generate a quadrillion tests. We just need to generate a small set of tests that guarantees every possible pair of features has been tested together. And that number, it isn't a quadrillion. It's closer to 60. From a quadrillion down to 60, that is the true power of the craft you've just learned.
So let's recap. Today, you have learned the 3 great arts. First, the binary forge, that fundamental choice of include or exclude. Second, the spells and rituals, knowing how to manage your state carefully in different realms like C++ and Java. And third, the twin gem prune, how to conquer duplicates by sorting and skipping. You can now recognize and solve any quest that asks for all combinations.
So here's your homework from the guild. I want you to take what you've learned and modify your forge. Your new quest is to find only the subsets that add up to a specific target number. Let's call it K. Go craft your code and share it in the comments below.
Apprentice Algorithm Answers, welcome back. I am NerdTeach, your guild master. Last time, we truly mastered the binary forge of subsets. But today we step into the crucible of order, a place where destiny itself is reshaped.
So let's just dive right in. Now, if you remember, our work with subsets was all about the art of choice. It was about what elements you picked. The order didn't matter at all. Well, permutations are the exact opposite. It's all about the art of the sequence. Here, the order is everything. Arranging the exact same elements in a different order literally creates a new reality, a whole new possibility. And today, you're going to learn how to forge every single one of them.
You know, for this powerful craft of arrangement, 2 great traditions exist. One is incredibly methodical and precise, while the other is just amazingly swift and efficient. Let's explore both paths. On one hand, we've got the path of the marked rune. I want you to picture a careful scribe, meticulously marking which runes have been used on an ancient scroll. It's methodical, it preserves order, it's precise. And on the other hand, we have elemental transposition. This is more like a swift elemental dance where we swap positions directly in place. Think of a mage transposing glowing orbs of energy with just a flick of the wrist. It's incredibly efficient with space, but a little wilder in its ordering. Okay, so first, let's walk the path of the scribe. This method forges our permutations using memory and, well, precision. It relies on a special ledger, what we'll call a visited array, to remember which runes we've already placed in our sequence. The incantation for this method is really specific. For each position we need to fill in our new arrangement, we scan our original set of runes. If a rune is unmarked in our ledger, if its visited spot is false, we claim it. It's ours. We mark that rune as used, add it to our current sequence, and then we call upon the same magic again. We recurse to fill the very next position in the line.
But listen up, because this is probably the most critical part of the entire spell. After a path is fully explored and our recursion comes back, we must perform the unmarking ritual. In our code, this just means setting visited back to false and removing the last rune we added. This is backtracking, and it is absolutely essential. It's the step that frees the rune, allowing it to be used in countless other sequences. Without it, we'd only ever forge one single path, and that's it.
And here's the big payoff for all that careful bookkeeping. The scribe's method has a brilliant advantage. Because it always considers elements from left to right, if you sort your initial set of runes, the permutations you create will emerge in perfect lexicographical order. That is, they'll be sorted just like words in a dictionary. A predictable and beautifully orderly result.
All right, let's switch gears and move to our second path. This one builds a completely different kind of power. This is the elemental transposition, a forging technique that's all about speed and efficiency, using almost no extra space at all.
This path really is a dance of positions. First, we fix a starting spot in our array. Then, we just loop through the rest of the elements, swapping each one in turn into that starting position. After each swap, we recurse, moving on to fix the next position in the line. And just like before, there's a critical backtracking step. We swap back. We undo the change. This restores the array, making it ready for the next element to have its turn in the spotlight.
So what's the deal here? Well, it's all about the trade-off. This technique is elegant, it's clever, and it is incredibly space efficient. We're talking O of 1 extra space. We're not making new lists or Boolean arrays, we're just manipulating the original one. But the price for all that efficiency is order. The permutations pop out in a sequence that isn't naturally sorted. It's a bit of beautiful chaos.
Now that you know the craft, you have to understand its power. And yeah, its peril. Every apprentice who decides to work with permutations must eventually come face to face with the factorial dragon.
Just look at this growth. The number of permutations for n elements is n factorial. Now for 5 elements, it's a totally manageable 120. No problem. For 10 elements, we jump to over 3.6 million. Whoa. But for just 15 elements, we are talking about 1.3 times trillion. The growth isn't just fast, it's explosive.
Let's just take a moment and let that number sink in. 1.3 trillion. That's how many ways you can arrange just 15 distinct items. The scale it's almost impossible for our minds to grasp, and it's for sure a massive challenge for our machines.
And that, my friends, that explosive computational beast is the factorial dragon. Its immense size is exactly why, in practice, and especially in coding challenges, we only even try to generate all permutations for small inputs, usually when n is 12 or less. See, taming this dragon isn't about defeating it, it's about having the wisdom to know when not to pick the fight.
So you might be thinking, okay, if this power is so dangerous, so computationally expensive, where do we actually use it, right? Why are we learning to wield a power that seems way too vast to control? Well, let's look at its real-world quests.
This magic is actually the mathematical backbone of cryptography. You know, a simple substitution cipher, swapping one letter for another, that's just a single permutation of the 26 letters of the alphabet. The total number of possible keys? 26 factorial. It's also used in cryptanalysis to search that huge space to break codes. And in software security, there's a cool technique called fuzz testing that permutes the order of inputs to a program, trying to shake out hidden bugs and security flaws. So I want you to remember this. When you're writing code to generate permutations, you're not just arranging numbers in an array. You're learning a fundamental technique that's used to build and to test the very integrity of our most critical digital systems. Okay, one final piece of wisdom for our craft, the echo rune dilemma. What happens if your input has duplicates, something like the array 1, 1, 2? Well, a naive approach would generate the same permutation multiple times, and that's just wasted work. The solution is a simple enhancement to our ritual. First, you sort the array. Then, inside your loop, you add a quick check to skip processing an element if it's the same as one you've already placed in that exact position during the current loop. This prunes all those duplicate branches from your search. Simple but powerful. You now hold the knowledge of 2 powerful forging techniques. The theory is complete, but you know true mastery only comes through practice. So, it is time for your guild challenge.
Here's your challenge. I want you to implement both the marked rune path and the elemental transposition path. Forge them in code. And then, think about the trade-offs. Ask yourself, when is the scribe's ordered precision worth the extra memory? And when is the elementalist's raw, space-saving efficiency the right tool for the job? In our next session, we'll tackle combinations, where the arts of choice and sequence finally meet. Share your forges in the archives below. Until then, may your code compile and your logic...
All right, apprentice algorithm answers, gather round. I am NerdTeach, and welcome. Today, you're going to face a legendary trial. This is a true test of your problem-solving prowess, the n-queens problem. So, yeah, we're diving headfirst into the n-queens problem. But look, this isn't just about finding an answer. No. This is about mastering the art of constraint satisfaction and that elegant, beautiful dance of backtracking. Make no mistake, this is the ultimate test.
Okay, so the rules of this royal challenge. They sound simple, but trust me, the implications are profound. You've got n queens and an n by n board. Your job, place them so that no 2 queens can attack each other. Simple, right? Well, that means every single queen has to have her own row, her own column, and her own 2 diagonals.
Now, I really want you to grasp the sheer scale of this thing. Just for a standard 8x8 board, if you tried to brute force it, you'd be sifting through, get this, over 4.4 billion possibilities. Billion with a B. That's not just inefficient, it's a total fool's errand. We need a much smarter way to do this.
And here it is. Here's our first big step toward that elegance. We're going to bring some order to all that chaos. See, instead of just throwing queens anywhere, we make one simple but incredibly powerful decision. Exactly 1 queen per row. And just like that, the problem transforms. We're no longer choosing n squares out of n squared. We're just choosing 1 column for each row. This one little insight? It's the entire foundation of our backtracking strategy. Okay, so to guide our choices, we're going to follow 3 sacred rules. Think of them as the royal decrees. They're what will protect our queens and stop us from ever making a bad move. First up, the column constraint. Pretty simple. Each queen gets her own column. Done. Then you've got the 2 diagonal decrees. No queen can share that top left to bottom right path or the top right to bottom left path with another queen. And since we already have our 1 queen per row rule, these 3 decrees are literally all the protection we need.
So you're probably asking, how do we even track these diagonals efficiently? Well, this is where the real magic happens. It turns out there are these super clever mathematical properties. For any major diagonal, the top left to bottom right ones, the value of row minus col is the same for every single cell on it. And for any minor diagonal, row plus col is constant. It's brilliant. This is how we turn a messy geometric problem into a super simple arithmetic one.
So what we do is, we use Boolean arrays, let's call them our magical ledgers, to keep track of which columns and which diagonal indexes are already taken. And what does this give us? It lets us check if a square is safe in constant time. An O of 1 check. That means no searching, no looping through the board, just a single quick lookup. This right here, this is the engine that's going to make our whole backtracking algorithm absolutely fly.
Okay, so now it's time to put it all together. We take our decrees, we take our magical ledgers, and we combine them into the core algorithm. I call it the backtracking ritual. And it really is like a dance. It's this recursive process of making a choice, seeing where it goes, and then, and this is key, gracefully undoing that choice if it leads to a dead end. So here's the ritual, step by step. In any given row, first you choose a column, any column. Then you constrain that choice. You check your ledgers to see if it's safe. If it is, you commit. You place the queen and you mark your ledgers. Then you recurse. You just move on to the next row and do it all over again. But, and listen up because this is the most important part, when that recursion eventually comes back, you recall your choice. You undo the move. You pull the queen off the board, clear the ledgers, and free up that spot so you can explore other possibilities.
So this is the first part of our little magic spell. We mark the board, place our queen. We've made a choice. Now let's see where this path takes us.
And here's its counterpart, the royal recall. This one simple line of code. This is the very essence of backtracking. This is what lets us explore the entire universe of possibilities without ever getting trapped down a dead-end path. It's the undo button that makes this whole thing work.
All right, for those of you who are ready to level up, for those who seek true mastery, there's an even more potent, a much more efficient form of this magic. We're going to leave our Boolean arrays behind now and step into the incredible world of bitwise sorcery.
Look, our Boolean ledgers, they're great. They're clear, they're effective, they get the job done. But bit masking, man, that is a whole other level. Instead of arrays, we just use single integers, and each bit inside that integer represents a column or a diagonal. What does that mean? It means we can check all of our constraints not one by one, but all at the same time, in parallel, with just a few super fast CPU operations. It is, and I don't say this lightly, a true masterpiece of optimization.
And this is the arcane formula at the heart of it all. I know it looks a little intimidating, but what it's doing is just incredible. In one line, it takes the bit masks for all the occupied columns, the left diagonals, and the right diagonals, smashes them all together with a bitwise OR, inverts that to find all the free spots, and then cleans it up with a mask for our board size. And the result? You get a new number where every single one bit is a valid, safe column to place a queen. You're finding all the valid moves for an entire row in a single lightning-fast operation. It's just, wow.
So, okay, we've mastered this ancient puzzle. But why? Who cares? What's the practical point of this royal challenge? Well, let's step away from the chessboard for a minute and move into the modern world, to what I call the industrial throne. So, really, why does this matter? I mean, what's the connection between some 19th century chess problem and the technology we use every single day? Well, the answer is surprisingly direct and honestly pretty powerful.
It turns out the mapping is almost perfect, almost one-to-one. Think about VLSI, chip design. The chessboard, that's your silicon wafer. The queens, those are high-powered components. And that no-attack rule we've been talking about, that's all about avoiding things like thermal hotspots and power issues. Same thing in parallel computing. The board is your group of processors, the queens are different tasks, and the rule is to make sure they don't fight over the same resources. So, you see, when you're solving the n-queens problem, you're not just playing a game. You are literally practicing the exact same logic that engineers use to design the layout of microchips and to schedule tasks on massive supercomputers. You're learning how to manage incredibly complex constraints in systems where efficiency is absolutely everything.
And so, apprentice algorithmancer, it is time. Time for your final trial. You have the knowledge, now you must forge it into real skill. Here is your challenge. First, I want you to implement the standard solution using those Boolean arrays. Really feel the logic. See that backtracking dance in action. Then, when you're ready for your master trial, I want you to ascend to the next level. Implement the bitmask version, and just witness the raw, incredible speed of bitwise sorcery for yourself. So I'm going to leave you with this final thought. You now wield the power of constraint, satisfaction, and backtracking. That's not a small thing. So look around you. What other puzzles, what other complex systems? I'm talking about everything from Sudoku to logistics, maybe even scheduling your own life. What else can be solved by turning it into this elegant dance of place and undo? The power is now yours. Go forth and conquer.
Apprentice algorithmancers, welcome. I am Nerd Teach, your guild master. We placed royalty on chessboards and forged every permutation imaginable. But now we face the ultimate constraint puzzle. Today, your training centers on Sudoku. So let's delve into its mysteries. Now, don't be fooled by its simple look. Sudoku is so much more than a game you find in the paper. This ancient 9x9 grade is a formidable test of logic and order, a true tablet of destiny. And our quest today, to learn the magic that reveals its one true arrangement. So behold the tablet, 81 cells just waiting for our command. Our mission is to fill every single empty cell, what we'll call a runic void, with the digits 1 through 9. But here's the catch. This can't just be done randomly. Oh no, we are bound by sacred laws. In the language of our craft, we call this an exact cover problem. And what that means is there is absolutely no room for error. Every single runic void has to be filled, and every rule must be perfectly obeyed to uncover that one perfect solution hidden deep inside the grid. These are the 3 laws of harmony, the sacred rules that govern the tablet. First up, row harmony. No rune can be repeated in any single row. Simple enough. Second, column harmony. Same exact deal, but for every column. And finally, subgrid harmony. You guessed it, no duplicate runes inside any of the 9 3x3 subgrids. These laws of balance, they are absolute. So how in the world do we conquer a challenge like this? Well, not with brute force. No, we use an elegant and powerful kind of magic called chronomancy, the ritual of backtracking. And with it, we're going to learn to test time itself. The ritual begins now. First, we scan the tablet to find a runic void, any empty cell. Second, we try to place a rune, starting with 1 and working our way up to 9. Third, and this is crucial, for each attempt we perform the harmony check to make sure we're not breaking any of the 3 laws. And fourth, if the rune is valid, we inscribe it, and then we recurse. We basically trust our future self to solve the very next void. At the very heart of our ritual is this harmony check. So let's break it down. First, we scan the entire current row. If the rune we want to place is already there, anywhere in that row, the check fails. It violates row harmony. Done. Next, you know what's coming. We do the exact same check for the column. We scan all 9 cells of the current column. If our chosen rune is found, this attempt is invalid. It violates column harmony. It's a simple little incantation, but it's a powerful guardian of order. And finally, the subgrid sanctuary. We have to check the 3x3 box that our cell belongs to. The little bit of magic to find the top left corner of this box is just some simple integer division. This lets us check that final law, subgrid harmony, and just like that, our harmony check is complete. So if a rune passes all 3 of those checks, we go ahead, we place it on the board, and we call upon our future self to solve the rest of the puzzle. That is recursion, and it's a profound act of trust in the process, really. It's a leap of faith that the path we've chosen is the right one, and our future self will figure out the rest. But you know, the real power of chronomancy isn't just about moving forward. It's the ability to go back. The true magic happens when that future self we trusted sends back a warning, a message that the path we're on leads to total failure. So just think about it. What happens when our future self gets totally stuck? It finds a runic void, it tries all 9 runes one by one, and every single one of them breaks a law of harmony. The path is a dead end. What can it possibly do when there's nowhere left to go? Well, it sends a message back to us, right here in the present. It sends back a signal. False. This path is wrong. And when we hear that echo from the future, we perform chronomancy. We erase the rune we just placed, turning the cell back into an empty void. We undo our choice. We effectively turn back time for that one single cell. And this illustrates the chain reaction perfectly. Look at this table. Our future self, deep down in the rabbit hole of recursive calls, tries every rune and finds nothing. So it sends a warning back to its immediate past, a false. Our present self gets that false, knows its last choice was a dud, so it erases that rune and tries the next one. But what if all of its choices fail too? Well, it also returns false to its past self, and the cascade continues. This is the echo of chronomancy at work, unraveling bad choices until a correct path is finally found. Now, you might be thinking, this is cool, but it's just for puzzles. Let me tell you, you've just learned a technique that literally powers our modern world. This ancient art of backtracking, it's a form of real-world sorcery. Let's see how this exact same magic shapes our world today. Okay, think about the massive challenge of scheduling nurses in a hospital. The tablet of destiny, that becomes the weekly schedule. The runes, those are the nurses. The rows and columns become shifts and employees. And those 3 laws of harmony, they become hard constraints, like making sure every single shift has enough staff to operate safely. But let's be real, the real world is way more complicated than Sudoku. There are advanced incantations, these really complex constraints. You've got union rules that demand rest periods between shifts. You've got skill requirements, like needing a senior nurse on every single night shift. For a big hospital, the number of possible schedules is, well, it's astronomical. We're talking more than the number of atoms in the known universe. These are all layers of equilibrium our algorithm has to respect. And yet, the very same backtracking logic you just learned is at the absolute core of the solution. Now, it gets an upgrade. It's enhanced into something called a constraint programming solver. Think of it as a more powerful form of our ritual. And it intelligently navigates that insane search space. It weaves through all these complex rules, it backtracks from conflicts, it swaps shifts, and it finds a harmonious roster for hundreds of staff members. That's a feat that would be impossible for any human to do efficiently. Your training in the theory of chronomancy is now complete. You get the ritual, you get the harmony checks, and you understand the art of reversing time. But, as you know, knowledge has to be forged into skill, so it's time to prove your mastery. So here is your challenge. Implement this Sudoku solver yourself. Then, for a true test of your new chronological mastery, modify your code so it doesn't just find one solution, but it counts all of the possible solutions for a given puzzle. What does that tell you about the nature of the tablet's destiny? share your most elegant incantations. Your drill begins now. All right, apprentice algorithm mancers, guild master nerd teach here. We have done some amazing things together, haven't we? We've forged subsets, permuted strings, and even placed royalty on their thrones. But today we face something totally different, our most dynamic challenge yet, the living labyrinth. So here's the quest. It sounds simple enough. Guide this spirit rat from the entrance, cell 00, all the way to the treasure hidden at the maze's exit. Now the rules are pretty straightforward. Cells marked with a 1 are open paths, and cells with a 0 are impenetrable walls. But, and this is a big but, you have to be warned. This labyrinth is not like the others. See, in all of our past quests, the path was always, well, forward. It was a one-way street. But not here. In these twisting passages, a new kind of danger is lurking, a peril that's actually born from having more freedom. In this maze, our spirit rat isn't limited at all. It can move in all 4 elemental directions, down, left, right, and up. And yeah, that freedom is incredibly powerful, but it also lays a pretty treacherous trap for anyone who's not paying attention. If we don't put the right protections in place, our poor rat is going to fall prey to what I call the specter of infinite cycles. Just picture it. It moves right, hits a dead end, then moves left, then right again, then left. It's trapped in this maddening, endless loop, forever lost. This is the big problem we have to overcome. So that really brings us to the key question, doesn't it? How do we give our rat all this freedom to move around without it getting hopelessly stuck in these loops? How do we actually banish this specter for good? To pull this off, we're going to need a special artifact from the archives. It's not a sword, and it's not a shield. It's more like a record, a magical logbook. We call it the Visitation Tome. And the thing about this tome is its beautiful simplicity and its incredible power. The Visitation Tome is basically a sacred matrix, a mirror that reflects our maze. Its one and only job? To record every single cell we step on during any single attempt to find a path. By marking our steps, we make it impossible to visit the same square twice on the same journey. And just like that, poof, the specter of loops is gone. With our tome in hand, we are ready to begin the path-forging ritual. This is the real magic, the core incantation. It's the recursive logic that's going to lead us straight to victory. The ritual starts by consulting the 4 directions, which we represent in code as vectors. Now, pay very close attention to the order here. Down, left, right, up. This is absolutely not an accident. It's a deliberate part of the incantation that will magically produce these perfectly organized, lexicographically sorted paths. Trust me, it's a tiny detail with a massive impact. Before our spirit rat even thinks about taking a step, it has to check what I call the 3 sacred laws of movement. It's a simple checklist. First, is the new cell we want to go to actually inside the maze? Second, is it an open path or are we about to smack into a wall? And third, the most important law for this quest, have we already visited this cell on this particular trip? We can only proceed if we get a yes for all 3. And this really shows you the entire incantation. At any cell, first, we inscribe our presence. We mark it in the Visitation Tome. Second, we look at all our neighbors and check the 3 laws for each one. Third, for any move that's valid, we go for it. We recurse down that path, step into the new cell, and start the whole ritual over. And finally, after we've explored everything from that spot, we perform the erasure of passage. I absolutely cannot overstate this. This final step, this erasure of passage, unmarking the cell in our tome, is the absolute beating heart of pathfinding backtracking. It is what separates one single failed attempt from total, complete failure. Let's think back to our End Queen's quest. When we placed a queen, her attack lines were blocked for that entire attempt to find a solution, right? Well, this is a totally different game. A cell might be part of a path that leads to a dead end. If we don't erase our mark when we backtrack, it's like we've put a permanent do not enter sign on that cell. It's now useless for all other potential paths that might have needed it. We have to unmark it to keep our options open. So we've navigated Fantasy Maze. And you might be thinking, hey, that's a fascinating puzzle. But what if I told you that this ancient logic, this exact same ritual, powers the beating heart of a modern industrial empire? This is so much more than a spirit rat in a maze. The logic we just uncovered is precisely what powers the massive fleets of robots inside those colossal fulfillment centers all around the globe. They're called Automated Guided Vehicles, or AGVs. You can think of them as real-world spirit rats. They navigate a massive grid, the warehouse floor. Their walls are pillars, shelves, and, most importantly, other robots. And their whole quest is just to bring products to human workers as fast as they can. But, just like our rat, these AGVs can run into a very, very expensive problem: deadlock. Just imagine 4 robots arriving at an intersection at the exact same time, each one blocking all the others. The entire flow of goods just grinds to a halt. So, how do they solve it? With something called deadlock resolution. A central supervisor system sees this gridlock and calls it what it is: a constraint violation. It then uses the exact backtracking logic we've been talking about. It commands one robot to reverse its path, to backtrack, which effectively unmarks its claim on those grid cells. And just like that, the intersection is clear for everyone else. The connection is just so direct and powerful, isn't it? The labyrinth is the warehouse floor. Our spirit rat is an AGV. The walls are pillars and other robots. And our backtracking incantation, that's the deadlock resolution protocol that keeps an entire robotic kingdom in harmony and ensures the eternal flow of goods. So, now it is your turn to step up to the forge. You have the knowledge, you have seen the ritual and its incredible real-world power. Your journey as a journeyman begins right now. Your task is to implement this pathfinding algorithm, but I'm going to challenge you to go beyond the basic quest. Can you make your code find all the possible paths, but present the shortest one first? And then, among paths of the same length, can you find the one that is lexicographically the smallest? And as you're forging your code, really think about this. When we say lexicographically smallest, we just mean dictionary order. Just like apple comes before apply. A path like DDRR comes before DRDR. So how does that specific order that you check your directions, that DLRU sequence, help you solve this challenge almost automatically? The answer lies hidden in the beautiful logic of recursion. And with that, we conclude our initial arc on pure backtracking. Just think about everything you've accomplished. You have forged subsets from thin air, you have ordered the unorderable with permutations, you have placed constrained royalty, and now you have navigated the living labyrinth. You are no longer an apprentice. You are a journeyman of the recursive arts. Well done. All right, apprentice algorithmancers, welcome back. You've already conquered mazes, but now we're going to decipher runic prophecies. Your quest is to dig out these ancient words hidden right here in this grid by connecting adjacent letters. It seems simple enough, but what happens when our dictionary has literally thousands of words? Let's get started. Okay, so here's the real trial. You've got the scroll of runes, this grid of letters, and right next to it, the tome of incantations, a dictionary with thousands upon thousands of words. The challenge, known as Word Search 2, asks us to find every single word from that massive book that's hidden in the grid. I mean, how would you even begin to tackle that? The first thing you'd probably think of is, okay, I'll take the first word from the dictionary, search the whole grid for it, then the second word, and search the whole grid again. And you do that thousands of times. This, my apprentices, is a one-way ticket to madness. It's slow, it's inefficient, it would take forever. There has to be a smarter way. We have to flip this problem on its head. So instead of just throwing our dictionary at the grid over and over again, we're going to forge a powerful artifact first. We're going to build a magical data structure that holds the collective wisdom of our entire dictionary all at once. We call this the Oracle Tree. So you see the difference, right? On one hand, you've got the path of madness, total brute force, checking one word at a time. But on the other, the Oracle's way. It's just so elegant. We're going to walk through the grid just once, and as we do, we'll let the paths we find whisper their secrets to our Oracle Tree. And the tree will instantly tell us if we're on the right track for any of the thousands of words it knows about. So how do we actually build this Oracle Tree, or as it's technically known, a trie? Well, we take every single word from our dictionary and we insert it, letter by letter. Each letter becomes a node in the tree. You can see how words like cat and car share the same path, C to A, but then they branch off. The real magic here is that this single tree now contains every possible beginning of every single word in our dictionary, all at the same time. Okay, our Oracle Tree is ready. Now, the ritual begins. This is what we call a synchronized divination. We're going to do a depth-first search on our grid of runes. But here's the twist. For every single step we take on the grid, we're going to take a matching step down a branch of our Oracle Tree. We walk them both together as one. So here's how the ritual works. We start our search anywhere on the grid. For each neighbor, we consult the Oracle Tree. Let's say we've traced the path CA on the grid. We ask the tree, hey, from the A node, do you have a branch for T? If the tree says yes, awesome, we keep going. If it says no, that's it. That entire path is a dead end for every single word in our dictionary. We just prune it and backtrack immediately. This is the source of our incredible speed. And this right here, this little piece of code, this is the incantation at the very heart of the magic. It asks two simple questions. First, have we already visited the cell? And second, does this path even exist in our Oracle Tree? If the answer to either of those is no, we stop. We cut off that path right there. This single check saves us from exploring millions and millions of dead ends. So how do we actually know when we found a word? Well, when our pointer in the trie lands on a node that marks a complete word, think of it like a glowing word gem. Boom, we found one. We add it to our list of findings, and then, and this is super important, we deactivate that gem. We basically tell the tree we've already found this word, which prevents us from finding it over and over again in the same spot. Now, you'll remember this from our maze challenge, right? We can't use the same letter twice in a single word. So, as we visit a cell, we put a temporary mark on it, a transient ward. After we've explored all the possible paths from that cell, we remove the ward and put the original letter back. This is backtracking. It cleans up after itself, allowing that same letter to be part of a totally different word later on. So, we've totally mastered the scroll and the tome. We can find any word with incredible speed, but what if I told you this wasn't just about word games? What if this algorithm, this whole way of thinking, is used to decipher the very language of life itself? And here it is, the big reveal. The principles we've just mastered, they aren't just for puzzles. They are foundational in the field of computational biology, also known as bioinformatics. The magic we've been learning has a massive, real-world purpose. Think about it like this. The runic scroll, our little grid of letters, is really just an analogy for a genome, a vast, complex sequence of DNA made of A, T, C, and G. And the words we're looking for in our dictionary, well, in the real world, they're not English words. They're something way more important. Scientists are on the hunt for what they call biological motifs. These are short, repeating patterns in DNA that act like biological signals or punctuation. A really famous one is the Tata box. It's a sequence that basically tells the cellular machinery, hey, a gene starts right here. Finding these tiny little motifs in billions of base pairs is like finding a needle in a continent-sized haystack. And this is exactly why our algorithm is so perfect for the job. You see, biology is messy. Patterns are rarely perfect. A motif might have a few mutations or variations. Our backtracking approach can be adapted for this kind of fuzzy searching, allowing for a few mismatches here and there. And when a genetic path starts to stray too far from the pattern we're looking for, the algorithm just backtracks, cutting away all the genetic noise to find the real crucial signals. So you've seen the power of this pattern, right? From a simple word game all the way to the blueprint of an organism. And now, it's your turn. It's time for your final forging. It's time for you to wield this power yourself. All right, here's your final quest. I want you to go and implement the Oracle tree, the trie, and then build that synchronized grid search algorithm we've been talking about. Grab a grid, grab a dictionary, and find all the words you can. Wield your newfound power and, hey, share your results. And just like that, you have completed the backtracking saga. You are not just an apprentice anymore. You are a master of constraint, of choice, and of recursive exploration. From finding subsets to solving puzzles, all the way to deciphering genomes, you now wield a fundamental pattern that builds our software and unlocks the secrets of nature itself. Well done. All right, apprentice algorithmers, welcome back. I am Nerd Teach. You've made it. We are standing at the final forge of our backtracking saga. You have learned 6 incredible arts, and today we're going to do something special. We're going to inscribe their laws into the grand tome of complexity. And look, understanding these core principles, that's the key. That's what gives you true power, the wisdom to look at any challenge, any problem, and choose the right spell to solve it. So let's open it up. This tome is our guide. It's a place where we can lay out all 6 of the arts you've mastered side by side and really see what makes them tick, their true power, and yeah, their true cost. First up, let's talk about the generative arts. Think of these as spells of pure creation. Their whole job is to forge every single possible combination or arrangement you can think of from a given set of ingredients. Okay, let's compare these 2 titans of generation. First, you've got subsets. Its complexity is O n times 2 to the n. So why 2 to the n? Well, it's simple, right? For each of the n elements, you have a binary choice. Is it in or is it out? That gives you 2 to the n total possibilities. And if we have duplicates, we use our twin gem ritual to just skip them. Now for permutations, things get a bit wilder. We're looking at O n times n factorial. Here, we're arranging things in every possible order. We use a simple visited check, our echo rune skip, to make sure we don't use the same element twice in one arrangement. So from that world of pure creation, we shift gears. We move to a world of elegant precision, the constraint arts. See, these spells aren't about making everything. No, they're about finding those very specific, very special solutions that follow a strict set of rules. And here we have 2 absolute classics. For n queens, the complexity is O of n factorial. Just think it through. You're placing 1 queen per row. You've got n column choices for the first queen, then n-1 for the next, and so on. But here's the magic. We prune like crazy with our 3-fold attack check. The moment a queen placement creates an attack, boom, we abandon that entire branch. For Sudoku, it's O of 9 to the power of m, where m is just the number of empty cells. For every one of those empty squares, you try the digits 1 through 9, and you prune with a harmony check. You know the drill. Just making sure the number works for its row, column, and its little 3x3 block. And for our final category, we have the exploration arts. These spells are all about navigation. They are designed to find a path, to forge a trail through some complex space, whether it's a tangled maze or a grid of letters. Now, these can look a little intimidating. For rat in a maze, a worst-case scenario could be something like O of 3 to the power of n squared. From any cell, we can explore up to 3 new directions we haven't just come from. Our key pruning here is the visitation tome, a simple visited matrix that stops us from literally running in circles forever. Then there's word search. Its complexity is O of r times c times 3 to the l. But this is where pruning becomes an absolute superhero. By using immediately, this one trick saves a mind-boggling amount of wasted effort. So, we've filled our tome. We've laid out the laws. But you know, just having the knowledge isn't enough. That's not wisdom. Now comes the real art. Learning how to choose and wield the right spell at just the right time. I mean, let's be honest, those worst-case complexities can look absolutely terrifying. But the secret, the true art of backtracking, is all in the prune. A single, smart constraint can take a massive, exploding search space and shrink it down to something totally manageable. Your real power isn't about avoiding the exponential, it's about taming it. It's about shaping it, cutting off those useless branches before they get a chance to grow. So, picture this. You're staring at a new problem, a brand new dungeon to explore. Where do you even start? What's the first step? How do you choose your spell? Well, you begin by asking yourself the 4 questions of the algorithm answer. First, is this a generative problem or a constraint problem? Am I trying to create everything, or am I just trying to find a few things that follow specific rules? Second, what is my state? What information defines a single step in my journey that I need to pass along? Third, what are my choices? From any given state, what are my options? What's my branching factor look like? And finally, the most critical question of all, how do I prune? What simple check can I do right now that will save me from a world of pain later? The moment you start asking those 4 questions instinctively, without even having to think about it, well, that's the moment you stop being an apprentice. And that means it's time for the Guild's final charge. Think about it. You started this journey just learning a simple binary choice, and you end it having designed constraints for royalty, solved prophetic tablets of numbers, and navigated living labyrinths. You're no longer an apprentice. You are a journeyman algorithmancer, a master of systematic search and deep recursive insight. And please, don't ever think these are just academic puzzles. They're not. These patterns are the hidden gears that make our world turn. They power everything from complex chip design to analyzing genetic sequences to optimizing massive warehouse logistics and even automating software testing. You now hold the keys to that machinery. So it's time for your final quest. I want you to enter the LeetCode dungeon, forge the code for these arts one more time, and then go conquer their challenges. Seek out problem 78, subsets, then problem 46, permutations. You'll find n queens at problem 51 and the classic Sudoku solver at problem 37. Go claim your victory and then come back and share it with the guild. This officially concludes our backtracking saga. But don't worry, the adventure is far from over. Our next great saga awaits, and we will be diving deep into dynamic programming, the art of remembering the future. Thank you so much for joining me on this incredible journey. If this saga has sharpened your skills, then lend your strength to our guild. Like the video, share the knowledge with others, and subscribe to the channel @NerdTeach. The guild truly does grow stronger with every single one of you. I am NerdTeach, and until our next saga begins, may your recursion always be bounded and your prunes be ever sharp.